Okay. Hi, everyone. Good evening. This week we had like very less time, right, to adapt for week 6 and 7. I guess I don't know whether are you guys ready with week 6 and 7. Uh, let us see. So we today we don't have much time, so we have only 2 hours to complete week 6 solve with us as well as week 7 solve with us. What I can do is for first 1 hour, we'll try to cover the questions from week 6. Whatever the remaining questions are there, I'll share that with you with the solution so that you can check back later, and then maybe in revision sessions, or we can discuss if you have any doubts there, right? And similarly we'll do it for week 7 also. Is that fine? Okay, fine. uh, okay, so I think let's start with week 6 first. I hope all of you have at least have seen week 6 lectures completely and have good clarity on week 6. Week 7 was easier week, but let us say if you didn't watch the lectures, I don't think you will have that clarity there. Is my screen visible?
Yes, sir.
Yeah. So shall we dive in into the questions?
Yes, sir.
Yeah, you can write down your answers in the chat box. Okay, I'll see them later. So this is the first question. Following chart plots MAE. What is MAE? Mean absolute error, right? Okay, that is mean absolute error, which against degree of polynomial features for regression task, which is the optimal value of a degree. So the features are having what kind of relationship here? Some polynomial, right? So that some degrees are involved. So by looking at this graph, so on the x-axis you have degree, and on y-axis you have mean absolute error. uh, so blue curve shows you the training error, and red curve shows you the test error. So you will have to see that, or you will have to answer for which is the polynomial degree by looking at this graph. So when we say that it will have that kind of degree, when what is the relation between train error and test error here?
The error should not be different between the training and the
Yeah,
test, right?
yeah. So
It
it
should be
should be like,
same.
yeah, it should be same, or the deviation is not much more. If it is much more, then so on the right hand side you can see that it is overfitting, right? Or maybe the high variance is there between the train error and the test error, right? So variance
Okay.
is much more, and that is not desirable, right? So the desirable thing, whatever is there, you will just have to write down there. Okay, say that. Okay. Uh, okay. Okay. Three people have responded. Okay. I think we'll move to the next question. Right. So you can see that for degree 1 the test error is lower, right? So you can see that red line is little bit below than the blue line at 1, right? Okay, so this you can see. So the optimal degree is likely 2 as it provides the lowest test error while avoiding the overfitting in at higher degrees. So 2 should be the correct answer.
Why
Why?
not one, sir?
So you can see, right, for degree 1 what is the issue? The test error is lower, that is fine. 2, the test error is the lowest before it starts to increase, right? What is happening here? What is the value of test error here at this point? Okay, test
It
error
is
is which
higher.
one? Which one
It
is
is
the test error?
higher. Okay.
Right? And what is happening here? It is start decreasing, right? It
Right.
is lowest at 2. So test error is lowest at degree 2, and similar at the same time, training error also was the lower, right? Correct, right? So here we can see whatever the argument we had initially, we can have 2 as the answer and 1 as the answer, right? Possibility is between 2 and 1. But if we should also see for lowest test error, right? So where here it is lowest, the test error is lowest, as well as it is not overfitting also, right? So that means the variance between the training error and the test error is also it's not much higher, right? That's why the degree 2 is the optimal value of the degree. Is that fine?
Yes.
Okay. Okay, the second question is, for ridge regression, if the regularization parameter is very high, which options are true? What is the for ridge regression, what W hat ML we use? So normal W plus some lambda times
Times.
length of the
W
W, right?
length square of
Yeah,
the W. Right.
yeah, norm of W square, right? So, so if the value of W is very high, what happens?
So A is correct, sir.
Okay, let others. Okay, just wait for one more minute, and then maybe we can discuss about it. So first option is what large coefficients are significantly penalized, uh, can lead to a model that is too simple and ends up underfitting the data. Uh, Large coefficients are not penalized. Okay, I think option C itself is like wrong, right? So, and option D is can lead to a model that is too simple and ends up overfitting the data. Okay, what does actually regularization parameter do to your W's? So why we are actually introducing W's? Sorry, lambda there, the parameter.
To decrease the error.
We have
To
some.
reduce W to 0.
So this was your mean squared error, right? Between the maximum likelihood estimator and the actual W's, and it depends on sigma square trace x transpose, right? That inverse. And I think we have somewhere uh, where it is added. Which slide it is having? Here, right? It's a regularizer here. So in the ridge regression case, we are having this loss function plus regularizer. So what does it do? If your lambda is too high, what happens? Okay, what happens if the okay this argument is to reduce w's, right?
Yeah.
Or
Yeah.
minimize this entire expression, which is a function of w, so that you'll get that w, right, for the entire objective function to be the minimum one, right? So this entire function is again a function of w, and if you have the lambdas higher, what does that mean? uh, will it penalize w's, or which w's it will penalize? So W's are the vectors of it is a vector of each of the coefficients to exercise, right? So what will happen if if your lambda is higher?
The W's will be closer to 0, right?
Yeah. So
Correlation will be more.
so in other words, what does it happen here in this case? So which are the coefficients here? W's are the coefficients,
Yes.
right? So if your W's are higher and uh, and if your regularization parameters are also higher, what does it do?
Regularization parameter means lambda or
Lambda,
lambda W
lambda, only
lambda.
lambda. Yeah, regularization parameter is only lambda.
So, sir, the D may be right, sir,
What?
because the correlation will be more. If lambda is more,
Hmm.
then
Okay, we'll see this one.
if,
This, yeah.
yeah. So if lambda is more, then the correlation will be less, because correlation is 1 by lambda. I mean, it's a reciprocal of lambda, right?
Okay.
So they'll be
Okay.
more
So
independent.
variance will be
Then
less. Variance
variance,
will be less means the parameters are close to 0.
uh,
Parameters will be close to zero.
variance will be less. Correlation will be less means variance will be more.
Okay, in other words, can you just see this statement? This is the objective function, right? And suppose your objective function have some coefficient associated with it. If your coefficient, so lambda, think it as a constant. If your constant is like, if your large constant is multiplied with something, what will happen when I wanted to minimize this thing? So that way your W's will go closer, right? Otherwise, you will not get the minimum of the W's, right? So is that correct? What I'm trying to say is
Yes,
understandable?
the
No, sir.
W should be close to 0, right?
Zero, yeah. So what will happen here? So large coefficients will be penalized.
Yes.
Large coefficients means what, sir? Large
W's,
coefficients.
W's, W's.
W's will be large. Means more.
Whatever the
It's
large,
more redundant.
it will get more redundant, right? Okay. So we'll see one by one what is happening here. Uh, First is correct. Large coefficients are penalized.
Yes.
Large coefficients are the W's. So whatever the larger W's are there with the lambda, right? What will happen is they will get penalized, and that's why because of that, it will become redundant, right? So let's say your values are like W1 x1 plus W2 x2 plus that expression is there, right? W transpose x is basically W1 x1 plus W2 x2 plus W3 x3 like that. But if you add this lambdas, and if your lambdas are high for any W, corresponding W's, what will happen? Whatever if you are having large coefficient, they will get closer to zero. So I think there is no issues with option A. What will happen to option B now? Is this correct? Option B.
Yes, sir.
Why it will correct? Why it will be correct?
Because when regularization is more, that is lambda is more than 1 upon, what is it? I don't know. What is it? Correlation coefficient symbol? I don't remember. It
Okay,
is 1
well,
upon some square, no?
1 upon gamma square.
Gamma square.
Gamma
So
square.
gamma square will be less,
Huh.
which means that the correlation between the variables will be less.
Let us say this is our actual thing, right? Let's say let's say W1 x1 plus W1, or let's say W2 x2 plus, let's say okay, maybe we'll see the higher degree thing, right? So is it fine, this one, let's say, and this is our normal y, right? And what we do generally, we'll add some lambda, right? So lambda here, which actually is based on, okay, I think this is the thing, and this entire thing is a function of W, right? What we are trying to do here is
It is square, no, sir?
so yeah, square, right? Because it's a vector, right? So W is a vector. Basically, if I wanted to write it down, it will be like this: lambda W1 square, possibly, plus
Square.
lambda W2 square plus this should be W3, right? Okay, now you are able to see this expression. Uh,
Yes, sir.
Now let's say if what is the objective? So generally, how we do the optimization, we'll find out its gradient, right, and set it to 0. In this case, x1, x2, x3 are what, or maybe x1, x2 are the like
Constants.
we should treat them as constant, right, because we know in prior. But what we have to actually so how this will look like, it will be like
So
del
x1
f,
square plus lambda, x2 square plus lambda.
right, no, and it should be equal to 0. So it will always be like what, yeah, x1 square plus
2 lambda.
maybe 2 lambda w1,
W1.
and
Yeah.
so, and that, let's say if I just take the first expression, it will be like x1 square plus
2 lambda w1
w1,
equal to 0.
right, like that. And similarly, if you just go ahead for other things also, it will be x2 plus lambda into so what if your value of lambda is higher, what will happen to w1? It will go down, right? Then
0.
only this, is that correct? So that's how it will penalize your w1s, right? Because we don't know w1, we are actually trying to get those kind of w1s. And if I say that, if I set my lambda, because this is a hyperparameter, right? Is that correct? Lambda is a hyperparameter, lambda is not a parameter, so we have to set some hyperparameter lambda. If your lambda is set to be high, then what happens to w1? It's automatically it will goes to
Low.
0, like it will comes close to the 0. But if it comes close to 0, so what will happen to this quantities also? Then what eventually, let's say if it this w1 w2 they will become insignificant, right? Is that correct? So if your lambdas are very high, similarly that will actually affect your coefficients of this, and then your model becomes too simple. And if your model becomes too simple, what does that mean? uh, Maybe your training error will be much higher than compared to the test error, right? Or sorry, not training error, training error may be lower, but the test error will be higher, right? And that will, okay, when this underfitting case will happen, you guys know about it, that graph of overfitting versus underfitting. That's a very famous graph. So I think for training error and let's say test error, right, something like this. This depends on what, let's say model complexity. What does that mean, model complexity? Have you heard of this terminologies before somewhere? Okay.
No, sir.
No, nobody. Okay, I'll just show you one graph possibly. Model. What do you mean by model complexity? Uh, uh, the model is generally like y equals to mx plus c. This is not a complex model, right? But let's say y equal to let's say ax square plus or maybe ax cube plus bx square plus. So as you go higher degree, like if your degrees are very high, right? That case it is said to be more complex model. Fine. So I'll just show you this possibly image. Which one is the good one? I don't know, but yeah. Okay. So where is your underfitting happens, and the this is also not a good one.
Is this in the lecture, sir? All
No,
this?
no, no, no. I'll just try to show you to visualize it better. Otherwise, it's not there. But it shows the same meaning actually. It's okay. I'm just trying to show you. Yeah, this is the better picture possibly. Are you able to see this picture? Uh, What is
Yes.
happening here? So as your model complexity increases, what do you mean by model complexity increases? The model is try to during training, what happens? Your model will try to fit that data. At least you know that part, right?
Yes.
All of you. Okay, so suppose you have the data like this, which, let's say, this is what the uh, linear model, right? Suppose it is mx plus c, and if I increase the model complexity, what will happen? So let's say this kind of model complexity. If I this is a polynomial, right?
So this is
Okay,
overfitting, right?
Overfitting.
what is happening here? So your this is overfitting. We'll see it later, but currently what's happening here? If it is a training data set, during training, this model gives me higher error, right? The
Yes.
linear one.
Yeah, linear is higher.
But polynomial one, what it does?
Zero
It is
errors.
giving the, yeah, zero. So so it depends on, right? Let's say you have uh, some other function, right? So might be like slowly, if you increase the model complexity, it will try to fit that data set during the training. That means your training error goes it tends to decrease, right, as you increase the model complexity. Fine. But
But
what
test
happens?
error may increase. But test
Yeah,
error may
yes,
increase.
yes.
Yes.
So this is the diagram for that. So as your model complexity increases, initially test error decreases, but later on, as you like try to fit like regressively, the training error, it will definitely decrease, but the test error will increase. So this portion, right, the variance between the test error and training error, if it is higher, that is your overfitting. And underfitting is what? Both the test error and training error are higher, okay, but still it is not a good fit. Is it fine?
Yes, sir.
Yes.
Here, what is happening here?
So if errors are high, then okay, fit.
The errors are here. What is happening? The error, both the errors are higher, right? Training error also higher and test error also higher, but they're they are like close to each other, maybe. So that's what we have seen in the first picture, right? Here, is that fine? What happened here? The test error and
Both,
train error both were higher, right?
both are high. Yes.
This is the case of underfitting, but we chose, shall we, like, what we chose? We didn't choose this one, degree 1. We chose degree 2, right? Why?
Error is
Test error.
less and
Yeah, and
there is no uh, error is less for both and
yeah. So that
the
means we are okay with this kind of complexity in the uh, model, right? The test error was the lowest one at that point. That was the case. So similarly, we can argue for,
Sir,
yeah.
sir, it may sound stupid, but what is the degree of, I mean, in the first question,
Okay.
could you
Degree
go
of polynomial, right? Okay.
degree, value of degree? What is the value of degree here, sir?
Okay. We'll tell you. So, what is the polynomial? In the mathematics, we say that, right? So it's a I think
Okay, it is the degree of the
a
polynomial.
yeah. So this degree, right?
Oh, okay, I got it, sir.
N
Yes,
minus one and a n plus, right? So it is a degree of
yes,
polynomial.
yes, sir.
So here maybe if degree is 1, what does it mean? It is actually like simple flat, right? So x, maybe mx plus c. This is the polynomial with degree 1, right?
Yes, sir.
And let's say this is ax square plus bx plus c. So this is a polynomial with degree 2, right?
Yes, sir. Clear. Thank you.
Yeah. So like that, if you increase the degrees here, the that means you are trying to increase the model complexity. If you try to increase the model complexity, what happens? Your training error goes to 0, right? Eventually, but or it tends to decrease. But what happens because of that? The test error started increasing, because then uh, uh, that is not might be a good thing for the testing purpose, right? So similar kind of argument we can actually use here also for ridge regression, right? As
So
your
why is the second option correct, sir, here?
here, na? Okay. So what happens here now? If you are penalizing with the large value of the lambda, what happens? Your complexity
W's
becomes,
become
yeah,
yes, W's become close to 0.
0. That means your model complexity also tends to become it is becoming simpler and simpler, right? Now that may end up in underfitting your data, and if you're getting you know, so is it correct? Will that become simple?
Yes, sir. Yes, sir. Yes, sir.
You can agree with that, right? How it will become simpler? Because the coefficients will goes very low for the larger degrees, like wherever that means it's they, let's say they become 0. Think about it like they become 0, that means they get vanish. So your polynomial becomes very simple, and if it becomes simple, definitely it will end up in underfitting, right?
So it becomes 0 because lambda is too large compared to W. That's why.
Yes, because this was the relation, right? We have seen the relation like this.
1 by lambda is nothing but 1 by
The
gamma
gamma
square, and
square is
gamma is the variance in
of
the
between the
Yeah.
individual WIs.
W's.
Correct.
So
Not
if the
between the WIs, but for variance of individual WIs, right?
gamma
No.
is basically it's your gamma square
Covariance. It's a
covariance
covariance.
matrix, right?
Yeah, covariance.
So
So
it will have the variance also between itself and covariance a bit among the other values also, right?
Covariance is 0 because the WIs are independent of each other, right?
Correct.
correct.
Correct. So if then that means what? We'll have to look at its variance within itself, right? Within the values
Yes.
of W. So as
Yeah, but if
huh,
the covariance is less, no sir, that means they are
huh.
more independent. It means that W will be larger, no sir. Why it is like becoming small? That is my question. You'll have more number of W's, right?
More number of W's.
Yeah, if the correlation is less, it means that they are independent of each other, right? So
Okay.
each of the feature parameters are independent and they will be
Okay. What is W vector? It is like all set of, let's say, right? Is this fine?
yes, sir.
Like
Yes.
that? Fine. And it will be, let's say, WD. What does that mean? Your data set, how inherently your data set will have how many features,
D features.
right? So you will have, can I say that? I'll say that F1, F2 to FD features, and each of this X1 is a like maybe we'll try to stick with this X1 suppose, and it is a vector, right? Vector of features. Can I say that X1 or maybe each of Xi? I'll say that it will be some values, right? I don't know,
Yes, sir.
values related to these features, and they will be like so. This entire vector will also be a d cross one. This is also d cross one, right? What will be the covariance between this W or covariance matrix basically?
So it will be D cross D.
Lambda square in the diagonals.
So can I say that gamma square,
Gamma
not
square.
lambda
Gamma
square, right?
square. Gamma square.
Gamma D.
Gamma square. Gamma square.
Gamma
Yes.
square. So it will be gamma 1 square, gamma 2 square up to gamma d
Gamma.
square. So this gamma 1 square,
Not all the gammas are same, sir. All the gammas are different.
they
Yeah.
should be different, right? Because they are for W1s, right?
Okay.
And what is this W a constant? First place,
No.
it's a variable, and that is why it is coming this variance right here. This is 0 and 0. So
Yes.
basically, W1 is a variable. So if you recall from stats 2, what do you just so you take individual W1 here. How does how we are actually able to find out its variance? So we are actually assuming some distribution for W.
Yes, sir. 0 and
Now here in this case, we
gamma.
have already, I think, 0 sigma square we have assumed, right? So W1 is a
Gamma.
variable. Huh? Okay,
Gamma
gamma
square.
square. Okay, gamma square. Suppose. But how it is coming here? So we are saying that W1 is distributed like this, correct? And maybe there is some mean W1 here. W1 mean, right? And all these quantities are actually and okay, mean W1 is actually we are actually setting it to 0, suppose, right? But what we are saying that there are like a lot of W's here, and the relation among them is like this. It is all of them are ideally what it should be like. What we should know, we should know this W1 like exactly, right? Or we may wanted them to know exactly, but it's not like that. It is not the case. So now we are saying that this W1 might be 0, might be this value, might be this value, might be this value, or might be like all of these values. Is that correct?
Yes, sir.
And basically these W1s are the constants of each of these xi's. So W1 x1 plus W2 x2 are like that. We know the data already. We know, but we do not know the relationship among this data. And this relationship among this data will be defined by this W's, each of these W's. Now, what we are saying is, let's say with this function, like this function we have defined earlier. What was the function? Objective function we have defined?
W transpose X minus Y.
Let's say it was, so Y was generated, this label was generated given the data was W transpose X plus
Minus
Epsilon.
Just
Huh?
Y the
Minus
whole square.
minus epsilon.
Plus epsilon.
Oh, plus epsilon.
Plus epsilon, right? And epsilon is a noise, right? With some 0 sigma square, right? Now, what we are saying is, how do you, so this W is not a constant, right? It's a variable in this case. Sigma is constant. Yeah, because not constant, but we know its distribution. Yeah, but we know its distribution, right? For now, X is constant. Yeah, we can treat X as constant. But now, because of this W, we'll get the variations in this predictions of Y. Is that correct?
yes, sir.
Right. So now what we are saying is, if my values of W, and what function we try to optimize here now, or minimize here now?
Error function, sir. W
Yeah, so
transpose
that
W
X
transpose
minus
X,
Y.
what is
W
it?
transpose X minus Y.
X minus Y the
W
whole
transpose
square.
X minus Y. The
Y
whole square.
Square.
whole square. This function and across all the number of samples, we're trying to uh, minimize it here. Okay. But the problem occurs here is, suppose my W's, right? If they give me some uh, based on one data set, if I get some values of W, but they may not be the optimum values, right?
Yes.
It is possible. It is possible that we get some W's uh, if I look at only one data set, right? So what we have to do is we'll have to do it like that's what we understood it here. So let me show you the where is the slides? Okay, here is that fine until this part was fine, and
Yes.
we said that there is, since W itself is a variable, there is we can say that this W at ML, which is the parameter estimator for W, it also be a variable. It is not a constant. So how much it is actually, so that means this quantity W at ML minus W, there is some distribution over there, and the mean of that distribution will be we are getting it through the sigma square trace of this covariance matrix, suppose. Fine. So the
So
discussion,
which is the constant here, sir? W hat ML or
W is constant, right? W is constant. W is the true W, right?
Okay, okay.
Like that should be constant, right? It's a true W.
yes.
W hat ML is like,
W
as
is
you,
the W which minimizes the error function.
okay, this W at ML is the answer, right? XX transpose inverse XY. Is that fine? This is your estimator. But how this estimator will change? Why I'm saying this is variable? As you change the data, will this estimator value change? So
Yes,
your
sir.
initial data X and Y is given to me. If I use some training data, and if I find out its solution, that WRTML will be different than if I use some other data. So there will be some variation, right? So WRTML itself will have some distribution. And what kind of distribution it is having? This, right? Okay, so okay, don't worry about it. But at least you agree on this part. Like as my data set changes, the estimator for W will change,
Yes.
right? Because this W at ML is based on this X6 transpose and XY, right? So that pseudo inverse and XY. So if I change my values of in the data set, definitely my W at ML will change. That means W at
If
ML
we
will not
change the training data, then WML, W at ML will
will
change.
change,
If we
right?
change,
Correct.
yes.
And like so you can, so how will you say that which is the best W at ML? So what you have to do, you will have to collect like different data set, try to find out its values, right? And then find out its expected value. So that means find out its uh, uh, so you'll get some distribution, right? As you, I think we have seen in stats 2, we used to get some let's say samples, right? X1, X2, Xn, and we used to say that this sample comes from some distribution X, right? Or IIDX, right? And how we used to like during the parameter distribution, what you used to do, you take different samples, find out its values, and then you treat these values as variables, and then you find out its distribution. Is that fine?
Yes.
A similar thing we are actually doing here. Now the question here is, I got this W at ML somehow. I need to, so there may be changes in the W's itself, right? So how this W at ML is varying from W, like how much it is varying from W, it is given by this quantity, sigma square into trace of this X6 transpose inverse. Is that correct? Sigma square can
So,
be changed. Yeah.
so what is this W? The W which we
It's
are
a
mentioning.
true W, actual W,
True,
for
from
which
where we got this W?
we are not getting it that W, but so let's say, okay, I'll tell you the thing. Uh, you have one data set like this, okay, X1, X2. Okay, how this data set will look like? Let's say X1, Y1, X2, Y2, and like that, Xn, Yn. Okay, these are n examples we are getting from. Let's say this is data set 1. Okay, there is another data set 2. It is X2, Y2, sorry, X1, Y1, sorry, and like that 2x and y. These are different values, okay? When I'm saying that data set 1, data set 2, these are the different values. Then we'll again have data set 3 like that, and again it will have some n values. Okay? You have the w's corresponding to it, right? So what we are saying that the y hat is what? The predicted value. The predicted value is what? I'm just saying that W transpose X, right, plus some constant. But I will stick to W's. So this will be, let's say, W hat, the W hat transpose X. Uh, what will be this predicted value for this data set?
W at ML.
1. Okay. Yeah, let's say ML1. I'm just writing down W hat 1. What?
So you are trying to say that the W which is the population W, whereas
Yes.
W at ML is
Yes.
the sample W.
Correct. So there will be some population, right? Underlying population for all of this data set generation. But
Okay.
we do not know that actual value. That W is unknown to me. Fine.
Okay.
And these are the some W's here. W1 hat, W2 hat, W3, and how many we'll get? We get some, and we can actually find out this W hat distribution. Correct? How can we find
Yes.
out the distribution? Because I have this W1 hat, W2 hat values. Now I have got some distribution for, let's say, I'm just, it is, we know, but let's say I'll just write down for the sake of convenience. There is some distribution for W hat, but now how can we check its goodness? Whether this W hat distribution is very closer to the actual W, the population W, right? That is what we wanted to find out. And I think we know the term of bias. What is the bias? Expected value of
W at ML.
Minus.
minus
Okay.
minus expected value of actually W, right? But since it's a constant, so we know that it is W. And if you see that this quantity is nothing but the it's only the square term you have taken. Otherwise, it's the same thing, right? Which I have written. So when we say this estimator is a better estimator, when your bias is or the best estimator is when the bias is equal to 0. And what does that mean? That this let's say ML hat should be equal to W. Correct?
Yes.
So that means expected value of W. So suppose this for like a different data set, we have said that we have got this kind of distribution for W hat. Sorry, I'm just sorry. This kind of, let's say, normal distribution we have got. And what is there on the x-axis? W hat ML,
ML.
right? And what is its? We are saying that this values, if this value is equal to W, the true W, and how much it is deviating from the W. So there will be like, yeah. So when this will be a good estimator for W hat ML, when your variance is the lowest one, right? If your variance is getting lesser and lesser, your estimator values will be very close to the actual values of W, right? So that means now we have got that it depends on what? The expected value depends on what? Sigma square and the trace of this matrix X6 transpose inverse. But the sigma square can we change? No, because we have assumed that the noise in the data set is actually a function of this sigma 0 and sigma square. So the noise is there, always will be there. So when we collect the data, the noise is already inherent to that data set that we agreed. So now the trace of this matrix, shall we do something for that? That was the discussion when it was started, right? And I think you go if you know it through the let us say you have got like this quantity.
So that's why you added something to the
Yeah.
XX transpose,
Yes.
so
Yeah.
that you get a less eigenvalue. And if you get less eigenvalue, the sum of the eigenvalues will be less.
And what happens
And
because of that? You're getting very closer. So your estimator is getting closer and closer to true W's, right?
yes, okay.
I hope all of you got this part. As so, if your lambda is higher, what happens here? If your lambda is higher here,
So
then
it
this
decreases the value of the
trace
eigenvalue.
trace, and if it
Eigenvalue
decreases,
and trace also.
so
Because
yeah, eventually if it's trace, so if it trace is decreases, what does that mean? This W at ML and W, that variance is getting lesser and lesser, right?
yes, sir.
I'm saying that variance because it's a variance, right? In like eventually. So if the values are getting closer and closer, that means your W at ML is basically becoming the true W, which is actually our desired thing, right? If I get the true W, then only I'm very confident about my predictions. Is that fine?
Yes, sir.
Yes, sir.
And this covariance matrix is gamma square here, right? So gamma square is the prior actually. So you are actually adding some prior. So what is MAP is showing is whatever we have discussed till now, how to introduce that the lambda I, right? So actually it is saying that this capital lambda should be equal to 1 upon gamma square. So this gamma square actually we are getting from the prior distribution of W. Right? So
So, sir, gamma square here we are considering as a constant. So
yeah.
this gamma square is the variance of the individual WIs.
Yes.
So here the variance of the individual WIs is considered to be gamma square, which is constant for all WIs, sir. Earlier you had said
It's
that
not
there is
it's not constant, right? It's a prior distribution. When it is a prior distribution for W, so W itself is not constant, right?
right.
We are actually getting that some gamma after this. Like if you follow this process, this MAP is what basically it's a Bayesian estimator, right? So is that fine? Bayesian estimator, when we calculate it is like likelihood into the prior, but this prior is for what? Prior for that W. but this prior W is a constant when we treat it as constant when we use the maximum likelihood method, right?
Yes.
In the Bayesian, okay, we'll just summarize. Okay, refresh your stats too possibly. So the estimator was dependent on or likelihood into prior, right? This is what actually this is the posterior distribution, right? Posterior distribution. But this posterior, so when I treat this prior is actually for a variable W, right? If I treat this W as constant, what happens? Then this posterior is only dependent on likelihood, and that is your maximum likelihood approach for finding out W at ML. But now if I say that this W will also have some distribution, correct? That is what we have seen right before some time, right? So if it is having some kind of distribution, and then now if you take that distribution into account, and how we will get that distribution, this prior distribution, from our data, right? So if you see that your data is having some kind of distribution for W, based on that data set, if I add this prior into the picture, then your posterior will be, this is a Bayesian estimator actually. Now this will become a Bayesian estimator, and then we, in this Bayesian estimator, we treat this W as a variable. In the likelihood estimator approach, we treat that W as a constant. Is that fine?
Okay.
Okay, I
Yes.
think, yeah, I think this little bit you'll have to you go through some lectures of stats too, possibly if you forget that part. Okay, then again, is it now going to make sense? This all four options. So option A and option C, is there any? So once option A is correct, then definitely option C should be wrong, right?
Yes, sir.
Option D. Okay, so
It is not overfitting. It is
yeah, it is going
underfitting.
to be underfitting. So that's why option A and B are correct options. Okay. This is a solution problem. Ajay has a data set that has a non-linear relationship between the features. The dimensions of training sample is 4 cross 2, excluding the additional all ones feature. Okay, for the bias term, you should add label vector is 4 cross 1 and vector. Okay, I don't know whether how much time it will take solve this. Are you going? Do you want to solve this part, or shall we skip it? I'll share you this.
So we'll just go through the approach,
Okay, fine.
not solve it. Yeah.
Okay, what is this question is saying here? Ajay has a data set that has a non-linear relationship between the features, right? Features and a label. What does that mean? So if you have X and if you have Y, how they are Y and X are related to each other?
Not linear. Not
Yeah.
linear.
So it will have, the X will have higher degrees, right? The dimensions of the training samples is 4 cross 2. What does that mean?
So four samples are there and
And
two
two features,
features are there.
right? So you can see here in the data set. So how your matrix will look like, your X matrix? 1, 2, 3, 4, right? And
Two,
1, 2, 2, 3.
two cross four, right? 2 cross 4.
Will it be 2 cross 4 or 4 cross 2?
Two rows and 4 columns, right, sir? We put the the data points in the columns, right?
Data
It's
points
always
in the columns or in the
the features we
rows?
put in the rows, right, sir? Features we put in the rows and the
Okay.
number of data points in the
The
columns.
columns. Okay. Okay.
So
Fine.
2 cross 4.
Okay. And how it will look like? Like each vector you are actually 1, 1, 2, 2, 3, 2, and 4, 3 in a row. Fine. Okay. I think that is okay. Label vector is 4 cross 1. That is okay. That is fine only. Weight vector is 3 cross 1. For all your calculations, consider sum of square as the X transpose W into Y. Okay. Why this W vector is 3 cross 1?
Because it has shrunk. Some are not there, right? W1, W2.
Okay.
Some one is 0.
Okay. And We'll discuss that part. What is question 1? Suppose Ajay has to compute the ridge loss value for this data with regularization parameter as 0.2. So what is the value of lambda here?
0.2.
2. Okay. What will be the value of the ridge loss? Correct up to 2 decimal places. Let us try to see that first, and then we'll go for the second question. This is okay. What is this? 1 1 1 2 1 3 and 1 4.
So they have added
Okay,
one
there
feature
one
extra.
bias term. So it is bias term is added. Fine. Okay, this is the normal our vector plus bias term. All of you are okay with the bias term, right? It's just
Yes, sir.
nothing but
3
like it's
cross
like
1. Now it becomes 3 cross 4.
yeah, that is okay. And then we have your W's, right? So that's how this W1 is for bias, right?
Okay, sir.
Bias term. 0.1 is for bias term. 0.2 and 0.3 is like normal our vectors. And is this a predicted vector? Y hat X transpose W, right? Actual Y's are here 1 1 2 2. So you will have to find out the loss
Different.
or
Loss
that some
function.
square error loss. This and what will be the ridge loss now? This is the loss after the normal linear regression we put it, right? And
Yes,
how
sir.
how will you add the ridge loss? So this is 0.2 here. It's a value of lambda plus length of this
W
vector, right? Length of the
W
W vector. So
Into
huh?
So why they have divided by 2, sir?
You can divide it by 2 or you can leave it, but I think for that it's to when you say this losses, right, it is always we consider for the squared losses. And if you minimize this quantity, what happens? If you remember that formula, like if you'll take a gradient, what will happen to it will become 2 times that, right, that quantity.
Yes, sir. So it
And
will vanish the.
to remove that 2 and 2, so that 1 by 2 is added extra, right? You can add, you can leave it. It's like same thing, doesn't matter much.
But if we don't do it, then we'll get a wrong answer, right?
yeah,
Yeah, yeah, that's yeah, that is okay. Like for answer sake you have to add, but I'm saying in general why it is added to there, because that in the theory, right, in the theory it is fine, right? In the theory, if you don't divide it by 2, that is fine. But okay, so if you are doing this answer, you just add it 1 by 2. Fine. Generally, you can divide it by 2, but if you look at the theory, it doesn't matter much because mathematically it's fine. Okay, that's fine. So ridge loss is fine. What happened
yes.
to lasso loss?
Same thing except L1 norm.
L1 norm. L1 norm is basically you just have to
Modulus.
you don't have to do square.
Here the second term has not been divided by 2. The first term has been divided by 2.
Where? Here?
In the
Here because
lasso one, the
yeah, why?
first
Because here it
because
is
the differentiation of the first term
yeah
is giving
2 times. Right, it is a square, right? So squared, whenever the squared loss is there, the 2 is actually divided to adjust that the 2 comes out when you do the differentiation. That's it. Fine, right? I think that is not a problem for us, but I hope you understand how to solve this problem. Because of this bias term, you will have to add one extra row here, which is 1 1 1 1, and this 0.1 is corresponding to. So how this is looking like? Let us, if I wanted to see, okay, x is basically 1 2 first vector. So can I say that this is x1? Okay, maybe I'll
yes.
write down
So
x1,
to add one bias term,
x2, yeah, 2,
2 2 or 3 2.
right, like that. So basically what happens here is I will have this w vector is looking like this. It's w0, w1 and w2. W1 and w2 are corresponding to the features, right? Not this sample data points. So if you add here 1, this will look like this: W0 into 1 possibly. Okay, I'm just for giving the example to understand it. Okay, W1 into 1 plus W2 into 2. What is this? This is W transpose X1.
Expect this prediction for the X1.
Yeah, for X1, right? Na?
For
And similarly, you will do
W1, for the Y1.
Y1.
Prediction for Y1. Yes.
Yeah. So for the first, which is coming out to be like that, and it is similarly we are actually approaching for others. That's why we'll have to add 1 here. This is X transpose W, and X transpose W and W transpose X actually, it should be same, right?
Yes.
Yes, sir.
Because it's commutative. The dot product is commutative. Okay, that's okay. We are at 9th slide. Okay, I'll try to finish it as soon as possible. Okay, can you just see this example? Bridgemont trains his linear regression model with 3 different values: alpha 1, alpha 2, and alpha 3 for the same. And what are these alpha 1, alpha 2, alpha 3? Learning rates. Is it covered here? Learning rate. You know what is epochs and all?
No, sir.
Epochs
sir.
is okay. Number of epochs is basically number of iterations.
Time. Okay. Time.
Okay, number of iterations you can say in the simple words. Like basically epochs comes for like batches. Have you heard the term of batch gradient descent? Gradient descent we have completed, right, in week 5,
Yeah, stochastic.
but not
Sir,
not
we
I
heard
think.
of stochastic.
Yeah, stochastic gradient descent is a kind of a batch gradient descent. Stochastic, what happens here, you consider each batch as one, right? Single training example, right? You do that, or okay, I think it's sir has mentioned as batch gradient descent as the stochastic one, right? What does it do?
So all this will be covered in the future, like
I don't think
weeks
so.
or so.
No, I
Okay.
think it is done. So it just came here, so I don't know. I haven't seen those questions, right? I am actually seeing these questions also for you. So let us see what happens here. You have it's not like it's already covered in the lectures, but it's not explicitly said to you. That is, I think, the difference. Uh, what is the gradient descent algorithm does for us? So WT1 equals to
WT
W2
minus
minus
theta
theta
Gradient.
at
WT.
WT, right? And eta is a
Step.
learning rate, or okay,
Learning.
sometimes it is called as a learning rate also. So learning rate, or I can say step size, right? If you have large training examples, it will be difficult for us to because what is WT? What is the solution for this is WT, or maybe I think for del F is what? I think it goes back to week 5, possibly. What is the okay? It depends
Gradient
on
of the
yeah, but I think it depends on your
XX transpose something minus X.
yeah.
XX transpose inverse,
Uh, b-
XX transpose W, XX transpose W
Minus
minus
2.
XY minus
Minus X.
W.
2X multiply by 2. That is
yeah, this is the part, right? Okay, this was the part. So basically this del f of W is 2 times XX transpose W minus 2XY.
2X.
That means you need to compute XX transpose all the time, right? In the gradient descent, why we are actually choosing gradient descent over the normal value, like normal this W star
We have to calculate because we don't need to
inverse
calculate inverse.
but still we need to calculate XX transpose, right? Still, if you have large training examples, still this XX transpose, because what is the dimensions of XX transpose in this case?
D
N
cross
cross N, right? N cross N.
D cross D. N cross N is X transpose X.
D cross D, sir.
Okay, okay, fine. Okay, D cross D. Let us say you're having large D's and N is also large. In that case, what happens? Still, this computation becomes difficult, right?
Yes, sir.
Yes,
And
sir.
what you do then? You go for
Okay.
Gradient descent.
yeah, stochastic gradient
Yes.
descent. Stochastic one is basically you just at one time you
randomly choose
do
some
some,
data point.
yeah, so let's say you do some batches, and you like you perform this gradient descent for, let's say you have like 1 to t, right? So t is what? Time steps, right? Basically, or maybe you can say that iterations, right? T are the iterations, 1 to t. What you do, you after t rounds, what is this part actually coming here?
Average of all the W's that we got in the T iteration.
So what you have done here actually, can you just tell me first, what is
We are going
WT?
in different directions, and we are hoping that after some T iterations, we are heading in the right direction by averaging all the W's.
Okay. Any other explanation to this? Understanding purpose, what is it? Like when I say for small t equals to 1 to t, what is happen at for t equals to 1? At that step, what is happening?
So we go in one particular direction, and the second step we go in another particular direction. Like that, in up to T steps, we go in
Why we
different
are
directions.
yeah, why we are going into different directions?
Because we are choosing some randomly
Yeah, correct.
randomly selected
Data
data
points.
points.
Yeah, so we are not actually using all n data points. We, let's say if I choose, let's say n equals to 100 here, right? So what happens here? Let's say you have 100 samples here. What you do, you just pick 5 samples. Maybe I say x1, x2, x3, x4, and x5. Okay, in the t equal to 1, you calculate wt for that. Okay, then what you do next, you again choose another 5. They may be x1,
Same or
x5,
different.
x6.
We can't choose same, no sir.
No, we
No,
can, because it's randomly selected from 100.
Oh.
That is what, yeah, that I think that's what why I'm doing this is because I failed that it, yeah, okay, but I think are you not saying here like x1, x5, x6, let's say x7, x8, fine, you'll find out it's wt, right? This is my second
So
step.
the WT will be the previously obtained WT, and this will be WT plus 1, correct?
No, right?
It's also WT.
Yeah, all WTs you will calculate, right? And then you take for
But
capital.
where is the descent, sir?
Huh?
Where is the descent then?
Descent we'll do it later, na?
111. Okay.
You first of all find out its WT stochastic gradient descent, right? This one, and then we use that one to do the previous step, right?
So in the next step to calculate the new WT, you use the WT which we got in the previous iteration.
One, yes.
Yeah, that's what I was thinking. But
Okay,
we are finding the average before itself.
See, here what we are saying, for t equals to 1 to capital T iterations, for each step what you do, sample bunch of data points uniformly at random and use the set of all points, right? And pretend this sample, yeah, correct. I think you're correct. What you're saying is correct. So every time you will find out, let's say next maybe WT plus 1, and then whatever it will come out, then we'll take a
Average of all
average
the
of it.
WT.
Yeah, fine. And that will, maybe it is a t plus 1, right? Okay, that is, but why we are
Otherwise,
actually,
it will descend only.
yeah, correct. But why we are doing this discussion, I just forgot. Yeah, okay. So what I was saying is, this alpha 1, alpha 2, alpha 3 are what? These are the learning rates. That means eta 1, eta 2, eta 3, fine. And you do this number of epochs is you can consider as number of iteration we do in the batches, fine. Okay. Now, which of the following correctly explains the relationship between alpha 1, alpha 2, alpha 3? What is the y-axis here?
Loss function.
So it's a loss function. So what happens as your epochs are increasing? What is happening?
Loss function.
Loss function is decreasing
For alpha 3.
Alpha 1 and alpha 2. For alpha 1 and alpha 2, the loss is decreasing, and for alpha 3, it is increasing.
Okay. Now tell me the relation between this.
So alpha 3 will be the biggest.
Alpha 3 will be higher.
Learning, we have maximum learning we get in blue one, right?
Maximum.
The blue one we get the maximum learning.
Okay. What is the?
Because the error is
What is
loss
the
function is less.
Yeah. So what is the relation here? between the learning. Let's say learning is basically how you are heading towards your, sorry,
So alpha 3 will be small. I mean, the maximum learning will be small.
right? So maximum.
We get maximum.
Alpha 2 will be the maximum learning. Alpha 2 will be the
Yeah.
maximum learning.
Yeah.
Maximum
And
learning,
alpha
it's
1
okay,
will be
but what about, okay? So you are saying that learning rate, right? It is higher.
yes, sir.
So
No,
what you are
the
saying that
maximum alpha 2 will be smallest.
no, see, if you okay, think about this. Let's say this is okay. I'll write down the equations here. Alpha 2. Right? So you are saying that if alpha 1 is higher, you are getting better at finding out WT plus 1. Is it correct? Now think in that way. So
So
basically,
smaller.
okay. I'll show you one example for it. How does this gradient descent works? Suppose you have this relation, right? Okay, between whatever the things are there. You start initially randomly, right? With some. If your alpha is smaller, what happens? You will
Go
slowly
downward.
decrease towards your minimum value.
Minimum.
If it is very high, what happens? It will,
Yeah.
right? It will sway
Yeah.
here and there. Is that correct? So you will have to choose the alpha such
Small.
that no, it might not, it shouldn't be very small. What happens if it is very small?
It will take lot of iterations.
Yeah, it will take a lot of iterations to reach to the value. So if you now you look at it, what is here? Think about, don't worry about number of epochs. Think about it as like number of iterations. So
So alpha 2 takes more more iterations.
but at least you can understand, right? So if you are having alpha as like very high, what happens? You might not get your loss function very minimum, right? It will like sway. It shouldn't be
So
too
for
high. It
green, the
should,
alpha is high. For the green, the alpha is high.
you are asking me the question or you are answering it?
Yes, sir. I am asking you.
Okay. Okay. It's okay. This will be your solution, Ram.
Yeah, green it is high because it is diverging upwards.
This is like simple explanation, right? So whatever we are discussing is the correct one, right? Alpha 1, alpha 2, alpha 3. Why? Alpha 1 is actually the red one. Alpha 2 is possibly, you know, this one,
Blue.
right? Blue, and alpha 3 is this. So if you have like very high, uh, so right, so if you have higher, what happens? You will not reach to minimum,
Minimum.
right? It will like sway. If you have too low, what happens? It will take a lot of time to reach, but it will not converge again in that case also. You should have some optimum alpha. And if you see this relations now, what is the correct relation here given as? Alpha 1 is, so option A is the correct one, where alpha 2 is, alpha 1 is very less, right? And hence it is not
B
actually
is
reaching.
correct. I think the option B is correct in the answer.
No,
I
no,
think.
no. B, oh, acha, okay, B. Alpha win is the smallest one. So what, this is the problem, right? If you have very small also, it might not reach to your minimum very early. It will reach, but it will take a lot of time, right? Versus if you are having large alpha, what happens? Maybe it will, so you can see the green curve, it actually dropping here first, and then it is increasing, right? So that means
Yes, sir.
it will sway away. What happens to alpha 2 then? Yeah, it will starting, if initially it will like comes down very early, and then it will slowly start decreasing. But yeah, it is, there is a chance that it will go to the convergence earlier than the alpha 1. So we don't need the slowest one, and we don't need the very high learning rate. So we don't know, we don't require a low learning rate, and we don't require a higher learning rate. It's intermediate will give you the idea. Is that fine? I think that is your explanation here also. Green curve does not converge, and instead it will diverge upwards because it is too high. Red curve, it is actually converging but very slowly than the blue curve. is a lower learning rate. Correct? I hope it is understandable. It will converge, but it will take a lot of iterations to converge, right? Because of its since it is very low. And blue curve is, I think it's a optimum one. Fine.
Okay, sir.
You are able to see. I think these are some new concepts, right? Which are not, I think, covered in the. But I think what
Could this be asked in the examination?
no, possibly, but it's okay, right? We are anyway discussing, right? So it's not hard, right? Whatever understanding we are having, are we able to uh, answer these questions? That is the important thing. You are able to understand it.
Yes, sir, to some extent.
Okay, fine. It's okay. It will not be like this much, which is like completely
Sir, alpha 2, can you show
yeah,
again alpha
yeah.
2 curve?
It's a blue.
Blue curve, okay. That
Actually,
is
see,
giving the optimal.
this is actually this understanding you will get it once you I think you cover MLP and all, right. So if you actually work on data sets, this will actually give you the better understanding, right? See, here we are actually talking from the theoretical perspective, right? But basically, this all of these things comes through experiments. So these curves are not like somebody has drawn from the theory. It's like somebody has worked on some data set, like different data sets, and these curves are drawn later on. There's not number of epochs and all. It's not, I think, covered for you, so it's fine. Like these kind of things will not be there. Okay, number of epochs, which is like uh, not related to your syllabus, it will not be there. Okay, what about this? We have, okay, now we know this, right? We have discussed about this part, theta 1 and theta 2. So theta 1 and theta 2 are what? ML estimators, right? Different
Yes,
ML estimators. And what is this part? Can I say it is a bias square?
yes.
Yes.
So if this is a relationship, what do you think about the estimators?
Theta 2 is a better estimator.
Yeah,
Theta 2 is
because it is having the
lesser bias.
lesser bias. So I think option B should be correct one.
Yes, sir.
Yes, sir.
Uh, where is the solution? Is this a solution for? Yeah, okay. I think it is shown through the data set, but fine. It is not required. You can say that theta two is a better estimate, right? It's not this solution. I don't think it's required, but you can understand it, right? We have seen previously also. What about this? What is the question? Do you understand the question? You wanted to implement it?
Five-fold cross validation.
Can you
Five,
just yeah? So all of you can just write down
Five models, sir. Five models trained.
four,
how many models are
four,
trained.
four.
Standard linear
Five.
regression, polynomial, and Gaussian. By the end of the validation process, how many models will have been trained in total, right? Yeah. But no, you will have to think about all these three, right? There are three
Yeah, yeah.
regressions we have used for the same data set, right? Now,
Yes.
for standard linear regression, do you need to have the five-fold cross-validation technique? We can use, right?
Yes, so it depends on the number of data points.
It doesn't depend on what model
Model.
you are using, right? So here, how many models we are having?
Three models in
Five.
four.
Three models, right? Linear regression, polynomial kernel, and Gaussian kernel.
Into four, no sir. 3 into 4, 12. One is for test.
Okay.
One is for validation.
Validation set, and
Four
four
into
are for training. Okay.
and into three.
Okay. You guys can give me the answers. So write down our answers in the chat box. I'll give you 2 more minutes and we'll see. Okay, done. Let's see the answers if somebody has posted here. 15, 12. Any other answers? Okay, I think okay, let's see the solution. Is it correct?
No, sir, I didn't understand.
Yes,
So we
sir.
don't have to reserve one for validation. How
We
does it
will have to,
Even if
right?
we reserve one, we'll still have 5 models, right? Because we are every time we are selecting 4 different models, and like that we'll have 5 different sets of 4 models.
F1, F2, F3, F4, F5. Okay. For first time, let's say you skipped this one, right? F1. What will be your training?
Yes, sir.
Training will
F2,
be
F3, F4, F5.
Yes, sir. Yes,
F2,
sir.
F3, F4, F5, and test is F1, right?
Yes.
Similarly, for the
Validation is F1.
yeah. So actually, see, I think you okay, yeah, validation. Okay, you can say that validation also. Then you will have, let's say, F1, F3, F4, F5. Then you have F2 as validation,
Yes.
F1, F4. What is it? Sorry, F2, F3,
F1, F2, F4, and F5.
F4 and F5, F3, and similarly F4 and F5. So F1, F2, F3, F5, F1, F2, F3, F4. So how many for linear regression?
So
Five
like,
models.
yeah,
5,
five. Yeah, yeah.
and for kernel 5 and Gaussian kernel 5. So total 5 plus 5 plus 5. Total
Yes.
15, right?
Yes, sir. Yes.
Okay. Yeah. So shall we move to week 7, or you are enjoying this part? Okay, I don't.
Not
Let,
I
let, let, huh? You're not enjoying this also.
no, we don't remember. It's very tough, sir, for me. Week 3, I don't know.
Week 6?
Week 6.
Yeah, yeah. No, it is tough. For the first time, it is tough. It is. I will not say it is like very easy. The only thing is, again, you guys don't get like much time, right, after quiz also. So that also is a part. You'll have to again study, right? You'll have to watch the lectures again.
Yes.
Hmm?
So we can
But
continue.
I have watched the lecture recently, so some of the things was not there. I mean, like
No, not of the
that
things are
epoch
not there.
thing and all
Whatever.
that. It's a
Yeah.
epoch thing, and
Yeah,
then
epochs is not there, right? Yeah, yeah. Epochs, but see, epochs is like very common terms. When you learn, I think machine learning practices, MLP,
there was not much detailed discussion on
batch
the
gradient.
model complexity, that thing,
Yeah, yeah, yeah,
and
yeah, yeah. I understand.
there is MAE that was not there in the lecture.
Lasso regression, it is there, na? MA is a mean absolute error.
I'm not sure. So
Yeah, lasso is the
Lasso is
so
there. Lasso is there.
lasso is there. So lasso
no,
is
no,
basically,
MAE, maximum absolute error.
yeah. So
That's the
in
thing. Yeah,
MAE, I think we use, okay. What is
in
maximum?
the lasso. Okay.
Right.
Yeah.
So
So
maximum squared error. So sorry, maximum, not maximum. What is it? Minimum squared error, right? MSE is minimum squared error, which when you actually treat it from, let's say, I think yi minus, okay, however you can treat it, like it's fine, right? Um, and let's say I1 to n, and MA is basically this is maximum squared error. So not maximum. Sorry,
Minimum squared error.
minimum squared error. And this is
and the question, if the questions are in the
MA is
same
a
line, then we
minimum
don't
only.
need.
Hmm?
So
MA is
the
okay.
Minimum. All
yes,
minimum.
that go ahead.
Minimum error. Yeah. Minimum absolute error, right? Because
Okay.
the only thing is what are these errors? They are the ways or the means to get us to the solution, right? Like to get the optimal solutions for W's, right? Why we are actually interested in errors? Because whatever the prediction will be there and whatever the actual values will be there, we wanted to get some kind of relation, so that we should be able to reduce that error. So we can have that in linear regression case. What we try to do is, our goal is to fit the data set, right? So this was my data, and if this
Yes.
is the best fit line, so you just generally see the errors. These will be the errors, right? The projections of these data points onto that line, right? And whatever
Yes.
will be the errors. So you can, so these errors for these data points, can you, what you can say about these two data points? The error will be positive or the negative? Basically, it
Positive.
will, yeah. And for this, it will be negative, right?
Negative.
But we don't. So if you just add up all the errors, they might give you the zero value, right? But that is not the correct way to do it, right? We wanted all of these error to be positive, so that
Yes.
only we can be able to minimize it. So the best possible way to make any quantity to positive is, one is making it square, right? And then
Yes.
adding up. Or second is take the absolute values of those errors and add it. That's the only distinction, right? And because of that, you will have like different solutions. For when you get the solution for W hat ML as the same as that of minimum squared error, or MSE, is when you
But for W hat ML, the MSE is used.
no
MSE
W
is used, no?
no MSE, it will, your solution will be same as that of the solution of MSE for a WRTML when you think of that
The
noise
noise
as
is
the Gaussian one,
normal distribution. Okay.
right? And if you think of that, or if you assume that noise as the Laplacian, then your W hat ML and your whatever the error, like whatever the W optimal coming from normal your process is same, will be and that should be equal to this, right? You understand? You, I think all of you know, right?
So,
Uh,
sir, the error in case of Laplacian is what?
it should be equal to the error we got it from this quantity,
Mean squared,
mean
maximum,
absolute.
minimum absolute error.
Yeah, yeah. So this will be what, like, how you found out this one? You just take, let's say this is some function, right? What do you do generally? This function. What do you then take? Del f,
Differentiate.
yeah, let's say df by dw, and then you equate it to 0, and from there you found out w hat equal to xx transpose inverse or pseudo inverse xy, right?
Yes, sir.
Right, and this is actually same as that of w hat ml. This quantity is equal when we assume the noise to be uh,
Zero
normal
sigma square.
square. That is a Gaussian noise. If you assume it as a Laplacian
Uh,
noise, then
Sir, in this case, you have explained it so easily, but how much of, I mean, do you expect us to
no,
expand
no,
our knowledge by ourselves?
no, not required. You actually will have to do it. Eventually, you'll have to do it, right?
But sir,
So
in the exam hall, there will be no
exam,
muscle
no, no,
memory.
no,
I
no,
mean,
don't
we will
worry,
be
don't worry
thinking
about
so
it.
much.
No, don't worry. We'll not add those questions there. Okay. This is anyway you will have to learn eventually, right? That is for
Yes, sir.
that is
Yeah,
the truth,
that I know, but
because
but
MLT does
we
not
have
cover
to.
everything whatever is there in the machine learning, right? Sir has
So
tried
so
like everything.
so what will be the reference point? I mean, what should
No,
we
no, whatever
follow?
is
Is
there,
there
you
any
can.
book or anything?
Yeah, this there are 4 books I think sir has said, right? They are enough. But
Oh,
see, what I'll say is, from the exam point of view, we'll stick to whatever is there in whatever the content is there in the lectures. We'll not go beyond that. Fine. So don't worry about it. I'm just
yes, sir.
since this topic is there, so I know that's why I'm just trying to tell you. Otherwise, yeah. So there, okay, but
This is a difficult function to differentiate, right, sir?
yeah.
FW 1 by n absolute
Then
value of
how will you
it
do
is
that?
not differentiable actually.
No, it is, you can make it differential, right? You can make it piecewise function and you can do it, right? So how you work with the absolute value? Oh, sorry, I think I did it wrongly. It's not norm, right? It is the L1 norm, or you can think of either I have to write like this one, or otherwise write the this. This is what kind of like that. Y equal to mod of x,
Yes,
correct,
sir.
right? Mod of x graph will
This
be
is not
like
differentiable.
at
This is not
one point, at one
at one
x equal
point.
to 0, x equal to 0 is not, otherwise it is differentiable, right? So you'll have to make
Yes,
it a piecewise function and do it like, yeah. See, it's not easier. I will tell you. That's why
Or you take the, what do you say, sir has said about subgradient.
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 Yeah, that method is there. Subgradient method for the sake. So I think we have learned that, right? I think it is there. So that means
Yes, subgradient is there. Yes.
yeah, and that is actually related. The subgradient method, I think it is related to this part only. Mean absolute error.
So what can you say about the noise in case of this
Laplacian.
L2,
Laplacian.
L1 norm?
Laplacian. So I don't know the Laplacian. Okay, Laplace noise. So there is a distribution for like let's search it maybe. I don't know exactly how does it look. But let's say Laplace distribution. It's a complex one or yeah, it is little bit complex. It is having I think few distribution maybe PDF. Okay, this is like this. It's complicated, right? Little bit because its graph will be like this. Sir have mentioned I think somewhere, right? In the lectures also sir has mentioned. So this will look like some. It will not be like proper. Have
So
you done the
at the
Laplace
mean it is
smoothing?
not differentiable. At the mean it is
Yeah,
not
yeah.
differentiable.
But sir has covered Laplacian Laplace smoothing or something, right? In Lasso, I think so, but I don't know. Okay, fine, fine. So don't worry about it. If you are interested, you can go through all of this later on. But yeah, as far as this is concerned, my point is to get all of you to at least familiar with these terms. Fine. I'm not saying that you should know everything here.
So
Okay.
it is very interesting actually what you're
Yeah.
doing now. And it's also giving theoretical insights. Sir.
Yeah.
So
Yeah.
just watching the lectures.
Yeah, lectures. I see. I can do the same thing as in the lectures. Right? I can't do much more than that separately. So whatever is
So
there, I
this is
will
very
send.
good. This is very good, sir.
Okay. So this question 8. Let's say we'll finish this question 8, and then maybe we can go to week 7. Fine. So we'll have some questions solved from there also, and then we'll stop. Whatever is remaining, we can discuss later on. Maybe you go through all the lectures once again, all the lectures, try to get a better understanding, and we may discuss it later again. Okay, consider that the three weight vectors W1, W2, and W3 are learned for a six-dimensional dataset using a linear regression or regularized linear regression model. What does that mean? Six-dimensional dataset and W1, W2, W3 is what?
These are the W's we get in different
So each of
models.
xi will be of what dimension?
Six,
Each
six.
six dimensions. So you have six features, right?
Yeah, six features.
Yeah. So these are the
So one
W1.
seems
Hmm?
W1 seems to be of lasso because it has got three zeros.
Three zeros, yeah, because only in lasso we get the weight vectors to be 0, but is it possible to get w as zeros in ridge?
No, no, no.
It is possible. No, it is possible. See, it is possible, but you can't guarantee it, right?
Okay.
In lasso we can guarantee that it will go to 0. Fine, right? Hmm?
So but lasso definitely it will go to zero. Some
0,
features
definitely.
will go to zero.
Definitely, yes.
Okay. Okay.
Okay, so consider that the three weight vectors are learned for a six-dimensional dataset using the linear regression model or regularized linear regression model. I think we'll have to uh, see which one, right? So W1 can be coming from
Lasso.
lasso. W2,
Standard error reduction without lasso or ridge.
what about W3?
That is ridge.
Why we are saying the ridge regression? This W3 is ridge and W2 is not ridge.
Because in W3 they are closer to zero, whereas in W2 they are further away from zero.
Right,
The
right.
features are
Right. So maybe we'll see the graph which was there. I think that is a better. I think and that is the best one. I feel to understand. Right. So where it is. this 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 one, right? This gives a like very nice picture of, so w hat ml values will be higher, right? This will be the normal values, right, from the normal linear regression. W ridge will be lesser than w hat ml. Is that correct?
Yes, sir.
And what about the lasso? There is
It will
possibility.
be W ridge will be sir, W hat ML is the one which gives the least error, right?
It will give the
But
least
we
error.
want,
Yeah, it will give you the least
but
error.
but we want something which satisfies the second condition also, which is that less than theta, less than
So
theta.
you wanted to remove the redundancy in the features, right?
Yes.
So, or maybe the complexity of the feature. So you can, what do you mean by complexity again? So let's say these three are going away, right? So that means the features corresponding to it. Let's say which will be the features? Let's say x2, or not features, maybe uh, oh yeah, features, right? So let's say f2 and f3 and f4. So these features are
F4 and
actually
F5.
sorry, f1,
F4 and
f3, f4 and f5. These features are now become like are
redundant.
of no, they will become redundant, or and if, in the reach case what happens is the importance is like less importance are given to them. So that way we are actually finding out the better combinations of the features, so that it will actually help in our calculations also. Like if you have more zeros in your data set, or it will be better, right, always. So that is
Yes,
the
sir.
case. So W1 is coming from
Lasso.
lasso, W2 is normal regression. You can see the weights here, they are higher than both W1 and W3, right? Uh, and it is the case for everything. You can see that. So yeah, W2 is linear regression, W1 is regularized model, which is ridge one, and W3 is lasso. I think it is it wrong? Yeah, I think it is written wrong. It should be W1 will be here, right? And W2, W3 should be here. W3 is the ridge one.
Yes,
Okay.
sir.
Okay, I think how many? There are like few more slides left here. Uh, let's see first week 7, and if I if you have any issues, I'll share the slides with you. If you have any other issues, we can discuss it later on. Maybe few 2 or 3 questions more here. Fine. Okay, just give me a minute. I'll share the other slide.
But sir, in Lasso,
Hmm.
one question I had that ellipse,
Hmm.
cannot it touch any other point other than the
It can.
borders line?
It can. So it if you okay, maybe I'll share you that part also. Okay. Here, right? You can see this picture is actually having ridge, lasso, and normal, right?
Yes,
So
sir.
see, this ridge can actually touch it here. So, okay, how many features are here, we are having in this image?
Two.
Two features. One is along the x-axis, and along one is on the y-axis. So if it touches, so if the ridge and lasso, right, if they are giving the same kind of answer, then the ridge will also give you the 0, right? See, ridge can give you 0, can, right, but it is not always giving you some features 0. But the lasso, like most of the times it will give, like it will remove the features from that part,
So
right?
in Lasso, always we are talking about the square here for
Yeah,
Lasso.
yeah, see here,
The
rhombus.
ellipse will always touch at the corners only.
It will touch at least one of the features, it will touch, definitely.
It will always touch at the
Yeah,
corners only.
yeah. See, if it is not touching here, right, what does it mean here? Like see, okay, I, so how it is to be maybe you can talk about ridge. uh, is this a it when I say this is the region, right, this entire circular region is the region for ridge one. So does that mean it will touch to the circle, this ellipse, or it can go inside also?
It will not be allowed to go inside
No,
because That is the optimal point.
Actually, it can go inside, right?
But it will. You don't need to go inside
Go
because
inside.
it will touch at one point
Yeah,
at the border, and that is the one
yeah,
which we are fighting
fine. But
on.
this is entire region is a feasible region, right? This
Yes, sir.
entire the circular region is a feasible region. So it is not always this ellipse will touch to the boundary, right? It may cross to the boundary and go inside it, right?
But will it? But once it touches, immediately we reach our solution, right, sir? When it
Yeah,
touches.
but it see here in the picture you are able to see that okay it might touch there, but actual practice it is not the case, right? This will like uh, okay, so my this the possibilities are there, right? So why we are getting zeros there? Like when we'll get zeros there? Suppose this is your understanding.
My understanding was that in Ridge you will never get zero, but it will close to zero,
No,
but
no, it will
never zero.
no, no, it will get zero. I'll tell you how. Suppose this is the way, right? It is going fine. So let's say it touches somehow it touches here. Okay, let's say that. Can I say that it kind of it touches here
If
possibly?
it's a vertical ellipse along the y-axis, no, then
So yeah, so
But
let
if
us
it is a vertical ellipse along the y-axis, it will contain only one feature.
yeah, but
The
again,
WHML will be along the one feature only. So
okay,
it's a unidimensional.
let's say these contours are like this, and your lambda is such that because this theta is what? Theta is actually lambda, right? Like the parameter, regularized parameter. What if it touches like this, or it goes like this, something like that? I don't know whether
but
because
before that
this
itself, it will get normalized.
you are just saying that you might end up cutting here.
Yeah.
No, the ellipse will touch the circle at only one point, na, sir. Once it touches the circle,
Hmm.
that is the point we are looking for, sir.
Okay,
It will not be allowed to go inside because once it touches, that is the point we are looking for, sir.
so uh,
And if it is if this ellipse is along the x or y axis, that means that we are talking about a one-dimensional data set because W@ML is
ah,
along one axis
then
only.
the second will be zero. Definitely, the
Yes.
second feature will be zero. But okay, I think I'll okay maybe I'll so this should go inside. That is why what my understanding is that because these values can be anything. So this w's are actually dependent on they are actually upper bound by this theta, right? Okay. Okay. Maybe I'll talk about it maybe in one of the sessions later on. Fine. This theta is coming from where? It's on lambda. Okay. Okay. Fine. Fine. So for now, let's say our understanding is this one that if it touches the circle, it should close the solution, right? It should not enter into this part. What about this? The ridge one. So ridge is this boundary. What happens?
Square boundaries. Ridge is circle boundary, and
Yeah,
lasso
lasso
is
is a square
square
one.
boundary.
So what happens in the lasso case?
My
Uh,
question is, will it always touch at the corners only for
no,
lasso?
no, not. It's not possible. It is not the case, right? It can touch to the sides also, right? But it
But
will
if
try
it
to touch.
touches to the sides, then the features one of the features has to go to zero at least, right, sir? Because there are only two features. So one feature has to go to zero. At
The
least one
okay.
feature has to go
See,
to zero.
we are actually looking at here only two-dimensional case. What happens in the higher dimensions? See, that scenario we'll look at it, and then we can say about it, right? So will it always give you the uh, zero solution for some features, or it will be the lesser solution? Okay, so the decision boundary here is for lasso is inside this, right?
Square,
Inside this.
square,
So yeah, so when it touches the ridge regression boundary, it will touch one of the points on the circle. When it
circle.
becomes yeah, when it becomes the square boundary, what happens? Definitely it will touch to one of the corners, right?
Yes, yes. It has to touch to the
It has to
corners.
touch the corner
But
because the corner is the so okay.
Yeah, the outermost point it has to
Yeah,
touch.
right. So outermost point, right? So this is a circle, and these are the corners, right? So let's say these are the corners. So when ellipse is, when we are talking about the ellipse, before touching it here, right, here or somewhere here, it will definitely touch the corners, right?
Yes, sir.
No, sir, but it can touch the sides also, right, sir?
How?
It can touch. Suppose the ellipse is
That's
situated
some
in
other
such a way
angles.
Huh?
that it can.
Where
Suppose
it
the
is?
ellipse is slightly lowered. Suppose the ellipse is slightly lowered, then it will touch the side first, and it will not touch the corner in
Lower
that way.
means like you're saying that somewhere here. I don't know what you're.
Lower and right side. Lower and right side. If you
Then
uh,
will it not touch here?
it may touch the corner, but I am trying to say that it may even touch the boundary of
Yes.
the square also.
Okay. So okay, fine. I
Sir,
think
I
it's
think it depends upon that XX transpose. There's one parameter which we set to
huh.
one, right, for determining whether it's a
Hmm.
circle or an ellipse.
Hmm.
So that will determine the shape of the
Shape,
ellipse. Yeah.
definitely. That is the shape of the ellipse, right? That is the truth, right?
Yes.
Okay. Maybe we will talk about it some point later. Okay, because this ellipse is this one, right? W minus W hat ml x is
Yeah,
transpose
XX
into
transpose.
and equals to some that. Uh, so this will
Constant.
actually, these are all actually giving you the from where, like how this ellipse will start, right? So the minor axis and the major axis, it will depend on this. But okay, we'll discuss it somewhere some point later. Shall we start with week 7 first?
Okay, sir.
Maybe because we are like out of time. Uh, whenever we'll get time, maybe we can discuss all of this again, right? Okay, this is the simplest one. Uh, uh, I think week 7, which I feel. I don't know what about your feelings. Can you just tell me? Okay, this is your data set. How many input features we are seeing here? 3,
Yes, sir.
and one is the label, right? Y is
Yes,
the
sir.
label here, and that we are trying to predict. And is it a balanced data set or imbalanced data set? Okay, okay. I think we didn't talk about balance and imbalance. Let's say, is it a pure data set or impure data set?
Uh,
When we said it is pure,
when all there are all zeros and but here in this case we are getting with trues also and false also, so it is impure.
it is impure. All of you guys
It is
agree?
impure.
The pure data set is like when your
All
labels are
all
all
zeros
ones,
or all ones.
or all zeros, or all trues or all false, right?
Yes,
One of
sir.
the class. This data set contains some impurity. Now, which of the following trees will give the zero misclassification error on the training data set? That is what given to you. In the trees, predictions are mentioned in the leaf nodes. And which are the leaf nodes? Like,
The
okay,
dark ones, the dark
yeah,
ones.
dark ones. Dark ones are all the leaf nodes. Uh, okay, so you will have to find out which tree. Are you guys able to see the tree properly, or should I zoom it a little bit?
Yes, sir. So
Zoom.
which of the tree will give zero misclassification error?
What does that mean? You are able to perfectly classify the data set into zeros and ones.
Okay. So the entropy should be zero after
What is
classification.
the first question here? Okay, for this tree,
B.
let's try to see. What is B means? B is 0 or 1, right? How many values each of this attribute is having? Only 0 and 1. So the question here
Yes.
is if B is equal to 0 or not, or maybe B equal to 1 or not. If B equals to 1, it will go this side. B equals to 0, it will go that side. That is the reading of this tree. Now just try to answer it. Take 2 or 3 minutes to solve this and then let me know. Fine. What is this answer? T2, T4. Okay. Are you guys solving it?
Yes, sir. I think T2, T4 should be correct.
Okay. So what is the first? What about the first tree? If b is 0, you should say y equals to t, right? So if that is the case, then how many data set will lie onto that side?
Three.
3, right? So x1, let's say I'll talk about, I will say each of this row as x1, x2, x3, like that. So first row is x1, second row is x2. So in that case, x1, x2 and x6, right,
X6, yes.
will be on the left side, and it will mark as t, true,
Yes,
right?
sir.
What about if it is once? What happens is, you will the question will be then, if
X3,
c
X4,
equal to
X5.
0, so among these three, x3, x4 and x5, whenever the ones are there, it will say as false. So for these two, x4 and x5, it will predict false, right? So what will be the misclassification error in this case? 1, or
It
maybe
will
say,
not be zero. It will not be zero.
yeah, that means there is a one misclassification happened, which is the x5. What about the t2? Let's say this tree. So if c is 0 and c is 1, so when c is 0, how many? So 1, 2, 3, first three examples, they will predict
Yes,
true. It's correct.
yes, sir.
uh, when it is 1, we'll have to check for a. So if a is equal to 1, it is f, and if a equal to 0, it is true. So that is giving me the correct predictions, right? So there is no misclassification happened in t2. Similarly, for t3, the first question is, if a is 0 or a is 1. If a is 0, we'll say it as true. So 1, 5 and 6 will
X5 and
mark
X6.
true. That
Yes.
is correct. When uh, a is equals to 1, in these three cases, we'll have to check for b.
B.
So if b is 0, it is saying true. So it is correct. But if b is 1, it is say f. So this
Misclassification is
x
there.
third will be misclassified if we traverse through the tree T3. For T4, again we have the question is at node A. So A is 0, it is true. Okay, that is fine. Then for once, if A is 1, we'll go for C. The question is now, if C is 0, we'll say true. Okay, and if C is 1, we'll say false. Okay, now the T4 and T2 gives me 0 misclassification errors. That means it is not misclassifying anything. I hope it is clear. Okay. Okay, I think people have left. They are getting. Okay, okay. Let's see. Okay, Manhattan distance. I think it is not covered, right? Consider
What
Manhattan
is
distance.
this Manhattan distance, sir?
It's one of the metric, right? So there are like 4 or 5 distance metrics. Like one is Euclidean distance, which we generally use. Another is Manhattan distance. There is another one is called Mahalanobis distance. I think one more is there. Like I know 4. There are like I think five or something. So
So how can you find out the Manhattan distance?
there is a
So
formula.
L1 is the Manhattan, no?
I think I don't know. I forgot the names, but let's see. Distance metric. Okay, but I think we shouldn't worry about it right now. We will not ask. If it is asked in the question paper also, okay, distance metric. Maybe we'll search for Manhattan distance. Yeah, this one. Right. So it is x1 minus x2 plus y1 minus y2, a mod of. So it's
Sum
a
of the absolute values.
L1 metric, right? Okay. So if I use the Manhattan distance, that is the L1 norm, the test point is this. this is the question: how many points are at a distance of 2 from the test point? The distance equal to 2. So how to calculate the distance equal to 2?
Sir,
What is the distance between this blue point and this plus
5,
point?
sir, 5. No?
One. It's just one, I think.
Total 5 points are there.
This is 1 and this is 2, this is 3. This 3 is also there, right? Total is 4, right?
So 5. Down plus 1, 2. The minus. The 2 minuses and the 2 pluses. The
Which one? This one?
yeah, that plus the top plus.
Okay,
and
this
then-
is 2, right?
Yes.
For this plus is 2 because along the x-axis it is 1, along
Yeah.
the y-axis it is 1. So this is 2. Similarly, this is also symmetric actually. So it is also 1 on the horizontal axis it is 1, on the vertical it is 1. So these two are having the, and same I think this plus, this minus and this minus will have the same. But for
And
this plus it is 1.
and one more minus, sir. The
Ah,
corner.
yeah, this minus and this minus, right?
No, sir, one more. The first row.
1, 2, 1, 2, 1, 2.
This one, yeah,
Yeah,
okay,
yeah, 1,
correct,
2,
correct.
1, 2.
Yeah, correct.
5 are there.
1, 2, 3, 4, 5. What about this? The distance increases, which is
It's
2
three.
plus 1, 3, and
3.
similarly it
Distance
is
is
3.
3.
So for this point, the distance is 3. For this, the distance is 2. For this, distance is 3. For this, it is 2. Here it is 1. Here it is 2. Here it is 2. And here it is 2. So using the Manhattan distance, the Manhattan distance means which distance? The L1 norm, right? So which is the absolute distance. Okay. Second question is, what is the predicted label of the test point if k equal to 1?
Plus.
Why? Because
What 2 is the closest point.
yeah, so this
2,
is
2
the
is the
closest
closest
point.
point and it is plus.
We are using actually one nearest neighbor to predict about the test point. So here this is the minimum distance. So and it is the minimum. It is a point which is with the minimum distance, and hence we'll go for this point. And whatever the class associated with this point, which is a plus class, positive class here, and hence it will predict positive class, right? Plus 1. Correct?
Yes.
Yeah. Okay. Okay. Can you just calculate this also? Will you be able to answer this part?
2 to the power 5.
2 to the power 5.
2 child nodes. Okay. Each node has exactly 2 child nodes.
What does that
Depth of
mean? Like
5.
you will have two questions, right? Only like you will have answer as yes or no. So each node will have two answers, yes or no. The tree has a depth of 5. Okay, I think we haven't discussed about that, right? Shall we see the answer then? If you
2 to the
2 to
power
the power
5.
5, I think.
It is
2 to the
correct.
power 5, I think.
Yes, sir. 2
correct.
to the power 5.
How many leaf are there, right? Okay, yeah. So with the depth of tree is 1 is like we'll have two nodes here, right? The depth of tree is 2. That means yeah, here like you'll have for the first it is 2, then 2 2. So it will be 2 to the power 5 like that to go, right? Fine. What about this? Question 4. KNN algorithm can achieve zero misclassification error with k equal to 1 on the training data set. Is it correct?
Can achieve 0 misclassification.
That means it is never going to misclassify.
Can achieve, no, sir.
No,
Yeah.
yes.
It can achieve? Think about it. Like, is it any possibility that you can achieve the zero mass classification error with k equal to 1? I think that this sentence is
No,
having some
it will
issues.
not. It may not give. It may give some misclassification, because the closest point need not be the one on the same side. The
We are actually
closest
not
point.
learning anything, right? First place. That's why
Yes, yes.
wherever the test point will come in, and if you check k equals to 1, I think that is a possibility that uh,
The nearest point may not be the point on the same side. It may not be having the same. Uh, that's what I. The
I think what
nearest point may not be the one which is having the same label.
hmm.
But it may
Sir,
also, correct.
sir,
It may,
maybe,
but it may not also.
sir, maybe it will give
This
error
can
for outliers.
Hmm.
Maybe it will give error for outliers as we are computing for k equal to 1. It will take distance for 1.
Hmm. Yeah, yeah, that is
The
correct.
word used is can, so it is right, sir. So word used is can, so it
Uh,
can achieve zero misclassification. Yes.
it can achieve zero misclassification error. Okay. Uh,
And decision trees can also achieve zero misclassification error. On the training data set, they are saying.
ah. Okay. So okay, we'll discuss A later. What about B?
Yes, it can achieve.
It can achieve.
Yes.
Yes,
What about C? K is a hyperparameter in K nearest neighbor.
Yes, it's a
yes,
hyperparameter.
Yes, exactly.
Yeah, definitely. Yeah, correct. What about option D? Distance metric is what is the distance
No,
metric?
no, no.
it is wrong.
Yeah,
This is incorrect.
incorrect. Okay.
Incorrect.
What about E? For K equal to N, the model will underfit.
Overfit, overfit.
Overfit.
It should be overfitting, right? Because yeah, it is trying to get all the uh, decisions. Decision trees are sensitive to small change in training data set.
Yes, sir.
Yes, sir. It is.
Is it?
It is sensitive to outlier.
Training data set changes, then the decision trees will also change, no, sir? If training data set changes, then the
Uh,
decision trees will also change.
decision tree will change, or the the
Values.
area error it is giving for.
On the base of the training data set only we make the decision tree, right, sir?
Hmm.
So if the training data set changes, the
Mhm.
decision tree itself will change.
Change. Okay. What about G?
Pure leaf, pure leaf is always one, right, sir? The impurity is zero for
And
a pure leaf.
impurity in this case, what it will be? Entropy, right?
Yes, yes.
So can it be one or cannot be? So entropy will be, for pure leaf, entropy will be one or zero.
Impurity will be maximum when half of the
Huh.
for a pure leaf. Okay.
Think about it.
Leaf cannot have any sub branches, right? So
It's okay.
leaf will always be either zero or one. So it is pure. It cannot have one.
It can have one, or what is the value for impurity there? It cannot be.
Leaf will always have the zero impurity, sir.
Sir, we will define impurity from that formula P equal to.
P minus. So what is that function actually? Like what is the curve for that function? We have seen yesterday, right?
Yes, sir.
This is your function,
Yes.
right? So it is actually what is P here?
1 by 2.
A fraction of no
Fraction of ones.
fraction of ones in a data set, right?
Yes.
Yes, sir.
In let's say label Y, right? So it is symmetric about half. And
So leaf is always pure, I
so
think.
these
Leaf
are
is
the
always pure.
this is like so the impurity actually is on the y-axis, right? Because I'll say that entropy gives me impurity,
Yes, sir.
or what is it?
For half the impurity is maximum.
Sir, for pure leaf entropy is 0.
For pure leaf, entropy should be 0, right?
Yes, sir.
And that means impurity will be so
1
impurity
for
of
half.
okay.
Impurity will be 1 for half and 0 for the extremes, 0 and 1.
Okay. So what about G? Is it correct or incorrect?
A pure leaf will always have either 1 or either 0, right, sir? So
Huh.
it will be always pure.
Always pure. Okay. What about option H?
Form a bounded region in a single dimension. We need it in a single dimension. Depth of 2. Yes, sir.
Yes.
Depth is the number of branches, number of the depth of the tree. Uh,
If the depth of the tree is 2, how it will look like? This one.
okay.
So
No, it
by
needs
looking
only
at this
one,
picture,
sir. The depth should be 1. In 1 only you can get 1 dimension. Single dimension you can get it in depth 1 only.
okay, fine. No, you'll just answer. We'll see the solution later on. What about
For
I?
depth 1 you will get in single dimension. For single dimension you need only depth 1.
Okay,
That's why.
I option I.
The neighborhood information becomes less reliable. Yes, sir.
Algorithm as dimension increases, neighborhood information becomes less reliable. What do you mean? Which dimensions it is talking about? Dataset dimensions or
I'm not sure, sir. K, I think I thought about K then.
no? I think it is talking about the dimensions of the dataset, right? What or
Okay,
is it?
dimensions of the data set.
So that means if you have uh, two data, like then it depends on what does that mean? Is it dependent on the distance? So if you have more dimensions, distance will be uh, same or different, right? Your
In
understanding
fact,
part
it should be more. It should be more reliable, na, in more if the dimensions
doesn't
increase.
actually it doesn't matter, right? How does it matter if you have more dimensions or less dimensions? Let's say if you are using the Euclidean distance, right? And if you put any test point there, how you say that? Let's say you have like three nearest neighbors. So how it will change? So whether it will change uh, the predictions if you have two-dimensional data set and the three-dimensional data set. If you have three-dimensional data set, reliability will increase on your. But what is it like? How will you say that? Fine.
It
Let's
should increase the reliability.
okay. Let us see the answers. For the KNN algorithm, we can achieve zero misclassification error on the training data set. This is correct, right?
Yes, sir.
Can achieve zero.
Yes, sir.
Uh, B, descent trees can achieve zero. Wrong. Hey, this is wrong, right? No, this is correct. Sorry, descent trees
Correct,
can
correct.
right, correct. What about C? K is hyperparameter. Correct. Uh, Distance metric is a hyperparameter.
This is wrong. We thought it was incorrect, sir. Distance metric, but
If
they are saying that it is a
yeah,
hyperparameter.
because no, I think see this is not like from our syllabus, but as you change the in if you see the scikit-learn, right, that library, in that case if you change that is a hyperparameter, you will have to choose, because what is hyperparameter? Hyperparameter is not trained, right? Like you can't get it from the training. Parameters you get it from the training. So whatever things which are not getting from the training, those are considered as hyperparameter. It's okay, that's fine. Okay, it is not in our syllabus, but you can think in that way. If you have different distances, and how will you? So their choice is dependent on us. So whatever is dependent on us, we'll have to treat them as a hyperparameter. Okay. What about option E?
Underfit. They are saying.
That is okay. This is correct. What about F? Sensitive. I think all of you have given the answer for this. I think it was correct. G. impurity of pure leaf cannot be 1. Yes, it is correct, right?
Yes, in a purely false samples belong to the same class. So
Yeah. And in decision trees, to form a bounded region in single dimension, we need a tree that has depth of 2 at least. So in a single dimension, example a line, we need a depth of 2 for a bounded region. Okay, you can
I thought that it require only one depth, but they are saying that at least two
single
depths.
yeah, single dimension actually bounded region you want, right? So that means you will have to partition in that data, right, somewhere. So you can think about like this, how your data will lie in this case, maybe like this, correct, right? So
Yes, yes.
so if you have one tree, that means you have half of your done, right? Is it bounded?
Yes, some on left and some on right. It is
This is not bounded, right? Like, so can you think of like this, like you have all the how this bounded region will look like? Can I say that this is a bounded region?
Yes, sir. Okay, but
that way,
it is open from above. No,
not above. It's not about above. Like this is
it
infinite
is
line, right?
bounded, right?
This is the infinite line, right?
Yes, sir. Yes, sir.
On both sides, is it infinite?
Yes, sir. Both
If you
sides
have,
is infinite, so
if
not
you
bounded
yeah,
on.
if you have one question, it will split into two questions, like two things, right? Let's say two partitions, but one partition is on one side, it is bounded, and another is sorry, unbounded, and another is unbounded on the other side. But if you have another question, now it will split, let's say maybe this side or maybe that side, but you'll get some bounded region right here. That
Yes,
is
sir.
the
Yes.
meaning of it.
Got
Fine.
it. Got
What
it.
about I? As
Source
dimension
of
increases,
dimension.
okay, I think it is not again, it's fine. So okay, that's, I think we'll discuss it somewhere later.
Higher
Don't worry about
dimensions
it.
reduce the reliability. That's
Yeah,
what they are saying.
yeah, correct. But that's fine. We'll it this is very important topic actually, curse of dimensionality in when you learn about machine learning. But okay, currently we don't have that part of it. So but you can you should have this in your mind, right? You maybe require to learn about this curse of dimensionality, fine. Maybe later on somewhere you keep it as your note and read about it. So lot of places it is very useful. Okay. uh, okay, now what happened now at the end? All the statements were correct, so there were no incorrect statement. Maybe I can say that I is not our case, but apart from that we were able to answer to all of the above here. Fine. So let us finish it quickly. Set K is a set of all the data points which will encounter question K. Select the possibility of question Q1 and Q2, so that set 3 is always an empty set.
He is always an empty set.
What is it asking here? So once you ask the question Q2, uh, you should not have any. So it should be empty set. So any data points will not uh, go into that set, right? Set one is the entire data set, right? Then you ask question one, you will get some for S you will get some data points splitted into yes and no, and some will be there in set two, and after that again you ask question two, it will go. So yeah, that way.
Greater than V1, less than. So second one seems to be incorrect. F1 is greater than V1 and then Fi is less than V2 and Vi is greater than V2. Second option seems to be incorrect.
Second is what? Q1 is, let's say Fi is greater than V1, and then Q2 is, so let's say if you are having V1 is greater than V2, what do you mean by V1 is greater than V2?
V1 is greater, whereas in Q1 we are asking that Fi is greater than V1.
So once we are asked
And
that part, then
once we go through the question 1, we'll
Mhm.
get we'll get Fi which is less than V1,
Less than
and
V1.
then in the second we are asking if it is less than V2.
Second option is V1 is okay. First of all, V1 is greater than V2. So if the question first is if Fi is greater than V1, uh, if it is yes, then what happens? All the data points which are above V1 will be there, right? Then
Yes, sir.
that V2, the question 2 is less than V2, does not qualify there. You're saying.
Sir, yes, sir.
So will that give me the empty set? Okay,
Yes,
okay,
sir.
the question, the answer, like the question is which one will give me the empty set? What about question 1? Oh, sorry, option 1.
Question 1 will not give empty set because F1 is less
Less
than
than
V1.
V1 and V1 is greater than V2. So then uh, there will be possibility that some of the data points will be more than V2, right?
Yes, sir.
That set will be there. So like that you will have to ask. I think there is a problem with this question is I think this Fi it is written, right? It should be F1, I guess, like, or some feature, right? Okay, fine. But answer 2 and 3 is the correct. We haven't gone through 3. What 3? 3 is similar to 2, right? Only here V1 is less than V2. That means this same question is there, right? Third also.
Yes, sir. First we are filtering out the less than V1,
Huh?
and then we are asking V2 is greater than V1, and we are asking if in the second question is if F is greater than V2.
V2. That
So
means nobody is
again
there.
it will be empty. Yes,
Yeah.
empty set it will be there.
Okay, fine. Okay, this is the last question we'll do, and then I'll share you all the slides again later on. Huh? What about this question 6? Class 0, class 1 is the red data points are the class 1, green data points are the class 0. Among the set of all linear functions, there exists a function which is sine of W transpose Xi such that the training error is 0, true or false for this data set.
So Wi will be perpendicular to the blue line, right?
Wi will be
Perpendicular to the blue line. So it should be minus 1, 1 maybe. Minus 1, 1.
where is this W transpose Xi line? W transpose Xi line is a blue line, right?
Yes, W transpose Xi will be
Blue
0
line.
on the blue line. 0
Huh?
on the blue line, and
Okay.
it will be positive on the for the green side, and it will be negative for the red dots.
So yeah, correct. So it will be negative for the red dots and positive for the because uh, the perpendicular line will be on that side, right? So that is correct. So
So W has to be perpendicular to the blue line, and the line perpendicular to the blue line is minus 1, 1. Vector minus 1, 1.
so no no regarding this question, what is the answer among the set of linear functions? Uh, there exists a function such that this is true. So will you get the training error at 0? That is the question.
Yes, we'll get training error as
Yeah.
0.
Why? Because you will get some line which will actually what it does. It will give you the perfect partition, right, between these two.
Yes, sir. Yes.
That is the question
And
actually.
W will be, I think, minus 1, 1 in that case.
Minus 1 1. You're saying where is that minus 1? Minus 1 1.
The vector minus 1, 1.
Yeah, that is yeah correct. That is also fine. Doesn't matter, right? Like I think any line perpendicular to this line.
Only line perpendicular is minus 1, 1 or 1 minus 1. Minus 1, 1 or 1 minus 1. Those are the two vectors which are perpendicular to the
1
blue
1.
line.
Yeah. Okay. 1 1. Yeah. 1 1.
1 minus 1. 1 minus 1.
1 minus 1 is there. That is correct. What else
And
you
minus 1, 1. Second one is minus 1, 1.
minus 1 1. Okay, the same line you are talking about actually. It's not a different line.
Opposite direction.
Okay, same line it is there, right? Okay.
Yes.
It is false. Why? Because is that a demarcator of? Oh, I think there is a problem in this question, right? X is a function and the running error is 0.
W transpose X plus C it should be, I think.
No, I think there is no problem here, right? The W
So, sir, I
transpose,
think the
yeah,
issue
yeah,
is that the line is not passing through the origin, I
zero.
think.
Yeah, yeah, it's not crossing. W transpose X is so the perpendicular line actually it should pass through zero, right? Only then we'll be able to say. Fine, okay. Maybe I'll talk about it later. I think is it there? Okay. How many questions we are left with? This is to find out the entropies. Do you want to solve this part, this question, and then we'll stop? 10 minutes.
Yes, sir.
Huh? All of you do it for 10 minutes, and then we'll stop.
Yes, sir.
Yeah. Set D has X data points. All the data points in D are made to answer question Q. The answer Q can either be yes or no. Dy is the DS and Dn is the dno. There are two labels 0, 1. There are 60 data points and labels are 1. So you can just solve this. Okay. You wanted to find the information there.
Okay, sir.
Yeah. We'll see the solution after some time.
So show the question.
Okay. Only three of you are remaining. Okay, three is not three. Only two.
Yes.
Okay.
It is two, sir.
Okay. Fine. Okay. So okay. Fine. Let us see. Have you understand the question? What do you think? There are how many labels are there in the data set with label as 0? So 60 are there with label as 1 in the capital data set capital D. What about the labels 0?
X minus 60.
Can you find out any information about it? No. From
X
here.
minus 60 will be 0, right?
So there are, let's say, what about this? Yeah, that is correct. So let's say I don't know anything about it, but can we infer about it? There are 12 data points with labels as 0 and dy.
And 36 has labels 1 and dy.
Huh.
So 48 points are there in
dy
dy.
data set. What about dn?
In DN, we have 8 data points as 0, but we don't know about the 1 points. So 1 is x minus 56 because if you
No,
can
Excel
count.
is required, right? 60, there are total 60 plus 1 already, I know. 36 goes into dy. So how many will go into dn? Is that
Okay,
correct?
right,
Huh?
right.
Can we right? So let us say this complete data set with 60. I know 61 data points, and let's say I don't know x is 0. Suppose, right? There was one question, and I have let's say yes and no, right? No, if you don't find out the data set, then you will not be able to solve, right? So ds will be, it will comprise of how
What
many? 36
36 is
1
1,
and 12,
and this
12,
will, yes,
12 0, right?
yes, sir.
12 0,
And
and d no.
24 will be yes, 24 will be 1, and 8 will be negative.
24 because the addition of this should be equal to 60, right? So
Yes,
24 will be 1 and 8 0 given to me. So total zeros in the data set are 12 plus 8,
12 plus 8, that is 20, right?
right? Now, now you can
Now you
solve.
can find it. Yes,
Huh.
sir, yes. Ze- 0, sir, 0.
What is
Gain is
the
0.
information given due to question Q, right? So
Gain is 0, I think.
information is gain is 0. No information you have gained.
Yes, sir.
What is the what? Okay, what is the entropy? how do you calculate entropy at this
Because
node?
all are having the same 60-20 3:1 ratio in all the three, sir. There is 3:1 ratio in all the three.
Okay, well, let me check. What is this, like 2 by 3? Not 2 by 3. It is like 60. What is the fraction p for this? It is 60 by 80, right?
Yes, 3/4 and 1/4.
3 by 4. So the entropy at D is 3 by 4 log of 3 by 4 plus 1 by
1/4
4
log
log of 1 by
of
4.
1/4.
It is at D, right?
Yes, sir.
Uh,
For yes also it will be the
DS,
same thing.
DS, it will, the entropy will be
Same.
entropy
Same.
because it is 36 by 48.
3/4, 1/4.
So it will again be the same, right? So I'll say that minus of 4 log of 3 by 4 plus 1 by 4 log of 1 by 4, right?
Dino also it will be same.
Required. Dino, will that be same? Okay, 24 by okay, I think I have written it wrong right here. Should
8.
say
Yes.
08, huh? So 32, total 32, right? So 2 by how come
Same,
it
sir.
is
1/4 and 3/4.
3 and 4? Okay, same. Right. So now what will be the information gain? So first place, how you can calculate what is gamma here? Gamma is
Gamma
ds
is
by
6
d.
by 10 and 6 by 10.
Total number of points in the data set, yes,
48 by 80. 48 by
48
80.
by 80. So how much it is?
6
6
by
by
10.
10 is 0.6. Okay, or maybe 6 by 10. We'll see. Then the entropy will be, or sorry, information gain. Information gain will be what? Entropy at D, let's say, minus
Gamma into
gamma times entropy of
D.
ds plus 1 minus gamma into
Entropy at
entropy
D.
at dno.
D.
And entropy of ds and dno are same. So
Yes.
entropy of
You can take it common.
d is here. So if I take entropy of ds common, so it will remain gamma plus 1 minus gamma. That will be 1. Right?
Yes. And
So
1 minus 1
entropy
is 0.
of ds is 0. So we are not gaining any information. Right? So yeah, that should be correct, I guess. Right. Fine.
You
So I
don't need to
hope.
calculate here. You don't need to calculate actually.
Why?
Because all the three entropies are same only.
Yeah.
All
So
D,
so
DS and D no
yeah.
all
So
same.
when we'll get the information when the entropy is reduced when you split that, because of that question, if the entropy is going to get reduced from the original thing, right?
Even this does not depend on gamma also. The gamma can be anything, but the entropy will be, the information
Yeah,
gain will
correct.
still be 0.
Gamma actually quantifies it, like how much you are getting. It's nothing doing anything else, right? Okay. So these are the questions. These are some, I think, theoretical questions below it. I'll share that with you, and you can see by yourself. For now, we'll stop. Fine. Is that okay?
Thank you.
Thank you,
Thank you,
guys.
sir.
Yes,
Yeah,
sir.
both of
Thank
you
you,
are
sir.
actually staying for the end. So, okay. Thank you. Thank you for joining.